Okay, I want to go over some of the tips on this practice exam. This isn't all of the things you need to know, so if you need to ask any other questions, just email me and I can explain why I did something here. So the first one, we're just finding intercepts, and the thing to remember is an intercept is on one of the two axes. So if it's on the x-axis, then we want y to be 0. In other words, we're not going up or down. So for finding the y-intercept of any of these, we're going to set the x equal to 0. Finding the x-intercept, we'll set the y equal to 0. So the first one here, not coming through real clear, but that's x equals 5. So x equals 5, you should hopefully recognize as a vertical line over here where the x value is 5 and y can be anything. So you'll see that that'll cross the x-axis at the point, and remember the intercepts are points. It'll cross the axis at the point 5, 0. So that's going to be our x-intercept. Now y-intercept, this one's a little tricky because you go to plug x in, you plug in 0 for x, which is what you would typically do to find a y-intercept, and you would get the equation 0 equals 5, which can never be true. And the reason that is, this vertical line will never cross the y-axis, so we say does not exist. Okay, second one here, we have a quadratic equation. We set that equal to 0, set the y equal to 0 to find the x-intercept, and typically, with a function anyway, x-intercept will be more difficult to find than the y-intercept. And we factored out into these two quantities. I double-checked distributing out the 2x and the 3, or the FOIL as many of you have learned. Then I set each of these, 2x plus 3 equal to 0, x minus 7 equal to 0, solve for x, get my 2x points. The y for both of those will be 0, the y coordinate, because it's an intercept. And then to get the y-intercept, I just plug 0 in for x, I get this equation, and solve to get y equals negative 21. Or you may remember this quadratic here is in the general form, and in the general form, that c at the end is just the y-intercept. Okay, and finally we have a linear equation. Fairly simple again, put the 0 in for x, solve for y. That gives us our y-intercept. Put the 0 in for y, solve for x. That gives us our x-intercept. Second question, we're looking for a domain of the function. So we have this function right here. Two things we're watching out for, a 0 in the denominator. So notice x cannot equal negative 3 because that would make this 0. Also making sure we don't have a negative under a square root or an even root. So we need that to be, we need 1 minus 2x, this thing underneath the root, we need that to be greater than or equal to 0. It's okay to have a 0 under a root. So we find that x is less than or equal to half, but x cannot equal negative 3. So x, the domain, is anything less than negative 3, not including, that's why we put these rounded here, very important, and this is the union, so this interval together with this interval up until negative half, and here we include, or sorry, positive half, we include the positive 1/2 because x could be equal to 1/2, and if you want to just convince yourself of that, put 1/2 into this. We'll have 1 minus 2 times 1/2, which is 1 minus 1, which is 0, and square root of 0 is acceptable. We just can't go any lower than that, which is why x cannot be higher than 1/2. Okay, here the difference quotient, so if you haven't done any kind of calculus or preliminary calculus before, this will just look kind of an odd plug-in of a function. If you have, you'll recognize this immediately as setting up for the derivative. So this is really preparing you for calculus, but it's using your knowledge of functions. So f of x we already have. f of x plus h, we just plug in x plus h anywhere that there's an x. Look carefully how I handle that where there's the squared term. So I plug the x plus h in directly for the x. We multiply that out, expand it, so this is f of x plus h. Now I'm rewriting the entire thing that I'm trying to find. So this is my entire f of x plus h minus that original f of x all over h. Then I'm simplifying, combining like terms, and I get down to this right here, negative 6x minus 3h minus 5. Okay, point slope form. Point slope form is really just based on that formula. If you remember, m equals y2 minus y1 over x2 minus x1, notice that all that we have to do is divide both sides by x minus, x2 minus x1. So that would bring it, multiply both sides by x minus x1. That would bring it over here. And the other difference is whatever that first xy coordinate pair is, we're leaving that as variables. So point slope form y minus y0 equals m times x minus x0. Something else to remember, this x0 and y0 are constants. These x and y's are variables. So we're plugging in to find the slope using our formula for slope, or just the difference in y values over the difference in x values. We get 5/2. Once we have that, we could plug in the point for b, we could plug in the point for c. If we wanted to, if we had another point, we could plug it in. I chose b, so I just plugged in 0 for my x0 and 4 for my y0, and of course I already had found the slope over here. That's how I get the point slope form. Okay, on number 5, solving in an inequality. So first, these can seem much more difficult, but really what we're doing is just distributing out there, collecting, putting it in the general form for quadratic, and then we have this less than or equal to 0. So we kind of put the less than on pause for a little bit, and we just keep that equality because we do know how to work with that. We take the equal sign, factor out, solve for x, and that's going to give us our zeros, or our roots, and it kind of lets us know where the parabola is. How do I know it's opening up? Because this value, this coefficient on the x squared term is positive. It's just positive 1, which means the parabola will open up. And now the final question is, how do I deal with that less than or equal to? So I want to know when this function right here is less than or equal to 0. Well, that would be anywhere right here, because everywhere to the left of that and to the right of that, I'm going to be above 0. But here I'm going to be less than or equal to 0. If I'm between -2 and -1, which were the two zeros I found here, and notice that I am including those points by using the square brackets, because it would be okay for these to have x equals -2 or x equals -1, because that would just give me exactly 0, which would be still meet the inequality. Okay, number 6. This is probably the most involved one. We have some function that we want to transform, and specifically we want to transform each of our nodes, each of our points there, and then we can just connect everything in between. So we have this original f of x, but we also have our g of x is going to be 1/2 f of x minus 1 plus 3. And I set up this chart. So these are the 4 original points. I'm using a instead of x because I'm reserving this x for my future function, for the transformed function. And so I'm pulling out here in this column just the first value of each of those original coordinate pairs. This x minus 1 is coming from the transformation that I'm going to be doing here, f of x minus 1. So this gives me the new x values. And essentially you can see I'm just doing a shift 1 to the right of the original x values. And then I find g of x. G of x, remember, is 1/2 f of x minus 1 plus 3. Okay, so I'm just substituting everything in, solving it, and now I have my new ordered pair, which I plot up here and connect. And if you're still uncertain about that, I would work through, the book goes through a couple examples, and then again, feel free to email me with more questions about that, what we're doing there. 7, so this is more testing your concepts if you know what's going on. So I want you to give me an example of a quadratic function with only one real root, and I even give you the root that I want it at. So if you think of this base quadratic function as y equals x squared, and I want it to have a root at -2, 0, but only one, the only way we can have just one root is if that parabola just touches the axis at one point. So what I want to do is I want to shift this entire parabola over 2 units to the left, and the way that I do that is I add 2 onto the x value before it gets squared. So adding to the x will shift me to the left, subtracting from the x will shift me to the right, and if that seems backwards, if you go back to the one before and try to work out one just with a, maybe take this 1/2 out and take this 3 out, put a square. I guess if the f of x is x squared, you don't even need to worry about that. But you can see using this process why it's going back the opposite direction of what you might think it would. Okay, second one, we want a quadratic function that has a maximum at 3, -2. In other words, we want the vertex to be at 3, -2, and we want it to open down. So shifting it 3 to the right means we subtract 3 from our x. Shifting it 2 down, getting that -2, means we add 2 to the y. You could also put a -2 over here, which some people prefer to do to shift the entire thing down, whichever it's equivalent in my eyes. And then we have to put this -1 right here to flip it upside down. So the negative on the x squared term will reverse the vertical orientation of the parabola, so it flips it upside down. And finally, we want a quadratic equation with a root multiplicity 2. What that's saying basically is we want to touch the axis and bounce off, if you will, which notice that we have right away. So any time in a quadratic equation that we just bounce off, whether it's opening up or if it's opening down, it's going to have a multiplicity of 2. If a quadratic function just has 1 0, then that 0 has a multiplicity of 2. Yeah. Okay, and let me break now, and I'll start a new video for number 8.